Vamsi, welcome to the Mr. Beacon Ambient IoT podcast. It's great to have you on the show.
Likewise, it's a pleasure to be here.
Well, as we were discussing, this podcast has been going for more than 5 years now, over 160 episodes. And we pride ourselves on having, a diverse set of technologies. It's not just about Bluetooth. We have competing auto ID technologies. And I think I have been fascinated by what the University of Washington has been doing with Bluetooth technology and with a technology called Backscatter, or a technique, I should say, called Backscatter. And University of Washington has created volumes of intellectual property. I know that your company, Jeeva Wireless, has got an amazing catalog of patents. And I feel a little bit conflicted because, Wiliot looked at Backscatter in the early days, and we decided to use a different technique. So I'm really looking forward to getting to the bottom of what is Backscatter, how it works, how it's applied, what are the problems that it solves, from talking to you. And hopefully we'll all end up a little bit smarter as a result of the conversation. So maybe I should hand the baton over to you. Can you just give us the elevator pitch for Jeeva? What does Jeeva do?
Yep. Thanks, Steve. So Jeeva is basically trying to reinvent the way people think and implement about wireless communication, wireless connectivity. So in a nutshell, Jeeva is commercializing a technique that you mentioned, Backscatter. And the basic idea is, how can we build ultra low power wireless connectivity solution? And that Jeeva does that by using a technique called Backscatter, where instead of generating our own radio signal, RF signal, that's what all radios do, we instead reflect existing signals to create data packets. So the way I like to sort of explain at a very high level is, rather than using your own flashlight to generate light, what if I use a mirror to just reflect an existing signal? And that way we can actually communicate at orders of magnitude lower power. So we're talking about implementing Bluetooth and Wi-Fi at 100 to 1,000 times less power. An added benefit of that is, not only is the power lower, but the solution would be smaller because the silicon required to implement Backscatter is very small. So think of RFID tags. That's what Backscatter does for you. You can have these tags costing a few cents. You can use them, you can throw them, you can reuse them, but they're going to be so cheap. And the fact that they're small, you can put them everywhere. So we bring that same benefits, but to Wi-Fi, Bluetooth, Zigbee, all the other protocols that people have built. So our idea is to use Backscatter, but stand on top of existing wireless protocols to basically build the next wave of ambient IoT computing, as you put it.
Very good. Well, thanks for that. And we'll drill into that in a little bit more detail. But you pointed out Backscatter is used in RFID at the moment. It's kind of a reflection, a remodulation of a stronger signal that you then reflect back. And I think the University of Washington has done some, and maybe we should explain, what is your relationship with the University of Washington? Then we can get into some of the applications and so forth.
Yeah, absolutely. So I basically was a PhD student when I joined University of Washington in Seattle in 2010. So I joined to study electrical engineering. And I joined Josh Smith, who was my PhD advisor. And then I also worked with Sham Golokota. Both of them are also co-founders of Jeeva, with two other grad students, Aaron Parks and Bryce Kellogg. So we have been, five of us have been working in this space starting, I would say, 2011, 2012. Mm-hmm. So University of Washington has a lot of expertise, as you mentioned, in Backscatter technology. And the lineage belongs to my advisor, Josh Smith. He used to work at Intel Labs back in the day, and then he came to UW in 2010. And to sort of give a little bit of history of where Jeeva came about, I think the genesis is this technique called ambient backscatter. So back in 2012, when we were all sort of early on in this field, and everybody thought of, oh, backscatter means RFID. So we were like, can we do more than that? Mm-hmm. So this was sort of a light bulb moment for us, which is, back in the day, Josh showed that you can actually take TV signals and harvest small amount of power from TV towers within a kilometer or within like 2 or 3 kilometers, 5 kilometers, depending on how strong it is. You can actually harvest that power, charge a small capacitor, and then you can do some interesting things with it. Like e-ink, you can probably transmit a packet maybe once every few minutes, once every 10 minutes or so, depending on how much energy you have. But then we were like, wait a second, it's interesting, but it's very hard to do anything with it because it takes so long to send a packet of data. We're like, if we have these ambient signals, we are harvesting them. Can we reflect them and do communication between battery-free devices? So that was sort of our sort of insight, which sort of started this whole field. And then in 2012, 2013, we actually published a seminal paper on ambient backscatter in SIGCOMM, where we basically showed that, yes, if you have two battery-free tags, those two tags can harvest ambient TV signals, but more importantly, they can actually use a small transistor, reflect that ambient signal, and do communication between two battery-free tags. So now you can, so our application was, if you're in a library, you you can put these tags. You don't have to put expensive RFID readers. If you have ambient signals, you don't need to coordinate anything. You don't need an internet backhaul. You can create your own sort of mesh network of devices which can talk to each other in a very free, ubiquitous way. So that was sort of the sort of the genesis of this idea of backscatter. And then we were like, if we can do with TV, then we extended that to Wi-Fi, Bluetooth, Zigbee, LoRa, all the other protocols we can think of, and sort of have this platform of technologies that can be used for a variety of applications.
And did you do something with cellular? I have this vague recollection of an article about using backscatter for cellular communications, mobile phones.
Yeah, so we have also done FM and cellular as well. So we actually use cellular for some interesting application. Like obviously we were able to harvest, but then we also tried reflecting cellular signals. We also, back in the day, I also did a very interesting project where basically you can use hand motions to change how signals are reflected from the body and use that as a way to gesture with the phone. So if you have a phone and if you want to just interact with your phone, like snap your fingers or like do kind of hand gestures, and because your cellular phone is basically recording, sort of monitoring ambient signals, then if you move your hand, it changes the signature of the signals, and then you can actually interact with them as well. So we have done a host of things with cellular signals as well, both harvesting and interacting with them or communicating and backscattering cellular signals as well. But as you would get into, I'm assuming a bit later, but cellular signals are tricky to work with because they're sporadic.
Absolutely. A lot of frequency hopping, and they also, the signal strength tends to fluctuate because those cellular engineers are super smart and they only broadcast a signal as strong as they need to. And so it's very challenging, very challenging.
Yes. Yeah, cellular networks are very sophisticated. They have to be because that's how we all can have like thousands of cell phones in one cell. And they do very precise power control, very precise timing, and that is unpredictable if you're not part of the network. And that was a challenge, and that's why we moved away from cellular to more popular standards like Wi-Fi and Bluetooth, where they are more free to control.
So how sophisticated can the devices be? And I'm gravitating in my mind to the beacon, the auto ID device, but obviously you can use this for other things. And I do want to get back to what are the applications. I don't want to assume that everything's a beacon just because this is the Mr. Beacon podcast. But so clearly you can remodulate a signal, you can bounce it back and encode different data in it. But how much, what sort of ability, if you're using backscatter, do you have to do more complex logic at the other end of it? It seems like if it's in the moment, then you've just got kind of this mirror and you're like flipping it this way and that. What about things like encryption and sensing and that sort of thing? Is that possible when you're using backscatter?
Yeah, absolutely. And I think maybe I'll take us one step back. So if you look at any IoT device, you have few different things that every device needs to do. So we talked a lot about communication. That's one piece of it. You will also have some computation, and you were talking about encryption, which is sort of sensing and computation, computation and communication. Then you also
Mm-hmm.
have sensing piece of it, and then power delivery piece of it. So
Mm-hmm.
the way to think about backscatter is how can you replace the radio with something else? So we can talk about concrete examples, but the way we look at it is it's a jigsaw puzzle, and all pieces have to fit together. And if you have a jigsaw puzzle where radio has a big piece in it in terms of say power, then can we replace that jigsaw piece and put
Okay.
put a backscatter in it, and then the whole jigsaw or the pie becomes smaller and more efficient.
Okay. So the other pieces of the jigsaw, if one piece, a central piece of the jigsaw is the communications bit, then maybe you can use other complementary techniques for the other pieces of the jigsaw. So I'm guessing that those could use a battery, or they could use energy harvesting, where you're charging up a capacitor, and maybe you do the computation over time or the sensing over time using that. So, do you have one of your devices here?
Yes. So let's see if we can show it
Yeah,
here.
yeah,
Oh
no,
yeah.
I see it. So, printed circuit board. Yeah.
Yeah. So here, what you see here is just a standard ST microelectronics MCU. It's a Bluetooth SoC. And then this is the piece that is new with our technology over here is just one switch.
Okay.
So, so this is an example of a device which has a Bluetooth SoC. It also has basically here you will see a gyro, like an ST 6-axis IMU, which has an accelerometer and gyroscope. So we are
Okay.
building like this new sort of interactive device, which basically is tracking the orientation and the acceleration of basically an input device. And the
Okay.
standard way is you use the Bluetooth radio, get data, establish a Bluetooth connection, and then you transmit that data over an antenna. So what we are basically doing is, okay, you are doing all those pieces, but your radio is typically, when it's transmitting a packet, it's going to consume on this board about 12 to 15 milliwatts of power, like peak power when it's actively
Yeah.
transmitting. And that's going
So a
to,
lot of people will be listening to this. Some people will watch it on YouTube. Some people will be listening on iTunes or Spotify. So for the listeners, then looks like it's about like 1 centimeter by maybe 4 or 5
yeah,
centimeters, and it's a printed circuit board, and it's got the normal chip. So this is not sort of in the world of Wiliot, then we just have stickers, but this is something that has got more chips on it. We just have a single chip. You have many chips there, and things like gyroscopes, which we don't do because that any chip like that is more consumes more power. So how do you power all these other chips that are okay? So you have a little battery here that is used to power. You just flipped it over, and I see the battery now for powering the sensors that do the gyroscope. But I'm assuming, so the benefit of backscatter in this context is just much longer battery life, because I'm not having to power wireless communications. I'm just having to power the sensing and the computation piece. Is that the general gist of it?
absolutely. So this has a CR1220. So if you don't use a radio, and if you're transmitting at say 120 hertz or so, which is the rate at you would need to basically build an application, this battery may only last a few hours. But if you use
Okay.
backscatter, and this is sort of, and I'll get a bit into the techniques of how we do it, but this is something we call an SoC retrofit solution. So as you pointed out, Wiliot has custom silicon, and we have built silicon for different implementation of backscatter. But for Bluetooth, we are going with a solution where our customers can just add, like I showed here, one switch and a
Mm-hmm.
firmware module running on the existing SoC that they already have. So
Okay.
this basically eases their deployment, because they don't have to build a new silicon into their product. They just have to license the firmware, one transistor, and then they can build their application, extend the battery life by 3 to 5 to 10x, depending on how they are implementing it. So
Okay. That makes sense. So, what are the applications that you've decided to focus backscatter on? Where are the sweet spots for you? Because you kind of described the venture capitalist in me was like, suddenly the matrix of different things you could do is like huge. So,
yes.
what did you decide to focus on?
Yeah, so I think that is one of the challenges of a startup, an entrepreneur, and especially if you're trying to build a platform. So this is sort of I think it's called the devil's curse in a way that we can do so many things, but at the same time
Yes.
you have to really focus. So the way I tend to look at, or tend to look at Backscatter is our focus right now is high data rate streaming. So we are really focused in electronic portable wearable space and trying to focus more on controllers. So if you have game controllers, AR, VR controller input devices like stylus, Apple Pencil. There are so many of these devices that use Bluetooth nowadays, but their battery life is somewhere between 8 to 12 hours, or maybe in some cases 24 hours. But it's mainly because the radio drains the battery. So we are focused on those applications to basically allow our customers to add this one transistor and basically upgrade their existing Bluetooth solution with a technique we call BT plus. So it's like we are adding backscatter to an existing Bluetooth platform and giving this capability of using backscatter. And that's also really beneficial for our customers because if they choose, they can still use a traditional radio because this ST chip still has a Bluetooth radio. They can still talk regular Bluetooth, but if they wish to choose and if they have the right application, they can turn off a switch and use our library and then stream data at using backscatter. So they get the best of both worlds. And those high data rate application for streaming audio or basically streaming accelerometer gyroscope information at 60, 120, 180 hertz, that's where the radio consumes a lot of power because you really cannot duty cycle the radio. If you turn the radio off, it doesn't matter. But if you have to always turn it on, then you can bring that power really low with backscatter.
That's great. So game controllers, stylus, keyboards, is that?
Yep, I think keyboards and mice and other input devices are also definitely doable with backscatter.
And what about remote controls for TVs?
Again, I think you're talking exactly the kind of application that we are looking at is basically all these controllers, TV remote controllers as well, which can all benefit from lower power. And then our sort of vision is like doing it in this way, where we add an existing switch and we don't have our own silicon, doesn't give us the 100 or 1000x that we can do if we have our own silicon. But that's sort of where we want to go to. But everybody has to iterate and get there.
Right. So that's where we kind of went separate paths, similar set of expertise and interest and so forth. And we went, we're going to design our own chip and we're going to go completely battery free and we want the sticker format. And you've found some, I think, very compelling applications where you could use other people's silicon. You've developed other silicon, so it's not like you don't know how to do it, but it's expensive to do that, right? So, so where are you at as a company? You've been, I think, going longer than Williot. So how many years has Jeeva been going for?
So we have been around for all 6 years now. So we spun out from university in 2016, summer of 2016. So it's been around six and a half years.
And so is it, what size company is it today?
So right now we are actually pretty small. So now we are a 6-member team. So we grew quite a bit last year and early this year, but then we, like all startups, we are facing some headwinds. So we have to sort of downsize a bit early this year. So right now we are 6 employees.
The core team. And what are you seeing in terms of, so you've been going for 6 years. I'm sure you've had a number of customers in that time. What are the ones where you've got the most, what do you look back on with the most pride and as the things that, are setting the direction for the company? What would you look back on?
I would say
maybe you don't need to name names, but the kind of projects.
Yeah, definitely. I would say our first chip that we built we started the process in 2019, and then we all know what happened in 2020. So we had some setbacks and challenges, but we got our chips back at the end of 2020. And then we launched our first commercial product. So our first chip is called Parser. which implements backscatter using Zigbee and LoRa at 900 megahertz. And that was focused on supply chain automation. And I'm really proud of the fact that we basically got to a product with first rev of the silicon, which is really, really unheard of. So I'm
Hmm.
really proud of the team and the kind of dedication we had to show, especially in the challenging times of remote work with hardware, which no pun intended, but was really, really hard. Distributed
Yes.
work. Plus, we had some supply chain issues as everybody else has faced
Yes.
during that phase. But our first silicon, it has bugs like any silicon, but it's
Hmm.
actually good enough to basically get to a product where we can actually transmit data while consuming a quarter of a milliwatt. So we are transmitting data packets at 250 microwatts, which I believe is the lowest power consumption of any commercial wireless connectivity solution that you can buy.
Very good. Um, and so, what it would be interesting to know, what was the foundation story? What was it that kind of tipped you over from you're doing your PhD, you have the academic life. What happened to make you decide to cut those ties and not go into teaching or whatever and do what you're doing?
So I think I've been a bit lucky in that sense that the opportunity presented itself. Because when I was doing my bachelor's back in India, I've always sort of had this dream of sort of, obviously, I was always interested in technology and doing research, but my sort of North Star was if I can de develop a technology and commercialize it, that would be the ideal career that I would like to have. And I
Hmm.
was lucky enough to work with so many great people, including Josh, Sham, Bryce, and Aaron, that we de developed this really, really amazing technology. We won a lot of best paper awards and stuff, but more importantly, we used to get basically we used to be contacted by all the companies saying, "Hey, this is really exciting. We have applications for it. Can we buy it, or do you have any plans of commercializing it?" And when so many people actually tell you that there is a market need, then it was really obvious for us to say that, yep, there is something here and let's give it a shot. And like I said, it's just something that I've always wanted to do. And when that opportunity presents itself, I didn't even think about it for a second. That was something I've always wanted to do, and I'm really happy that I chose that path.
And you've, I think, benefited a lot from the excitement around this technology. And looking at your site, you got coverage from CNN and The Economist. How did you get The Economist to write about you? What was the trigger for that?
I think I would say it's first of all, I think economists covered our passive Wi-Fi technology where we showed that we can basically transmit Wi-Fi packets about 10,000 times less power. So
Hmm.
I think there are two reasons for it. Number one, we built a very compelling sort of technology because ev- everybody who's listening to the podcast has had that experience when you have your phone and it's running low on battery, and it's mainly because your cellular or Wi-Fi is connected and it's sort of draining power. So that has been a problem everybody has faced. So I think
Yes.
that really struck a chord with the folks at Economist saying, "Hey, that's a problem we all face, and these scientists have solved it. So let's go and talk to them." And I think in addition to that, University of Washington is a great institution. We have a great track record, and they also do a really good job of sort of giving us the tools of how to present this story to the outside world, because our our basically research is funded not only by the university but by the National Science Foundation. So it is our duty as scientists to let the 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 people know what we are doing with the tax dollars as well. And being a public university, we have an obligation to sort of educate the world about what's coming down the line. So I would say a combination of doing exciting research and the fact that University of Washington has a really good infrastructure in place to get the word out were the reasons that we could get uh, coverage from CNN and Economist and BBC and other folks.
That is interesting. Yeah, my recollection of college, which is very fond, was we got a presentation skills training course, and that was it. So it sounds like there's something more at University of Washington. What did they do to help you do PR?
So they have a department who are, so remember this person, Jennifer,
Hmm.
who is a pro at it. Like, I mean, she knows how to write the stories. They also gave us, like, they had dedicated photographers and people who would come and shoot the demo video with us. They would do all the editing and they would create professional looking like videos that we will upload to YouTube. And then obviously we would get contacted by reporters and we'll talk to them and they would help us sort of uh, they would train us basically because if I give the same presentation that I give to my fellow colleagues at a conference, that's not going to fly with reporters. So I think those training, and it is a skill set that I immensely respect, the skill set that you need to have, and it took a while for us to understand how to say the right things. More importantly, like try to make sure that what we are saying is being presented in the way that folks can understand. So I think all those factors are contributed to basically us getting the coverage that we got.
Very good. Well, Vamsi, I've enjoyed this. Is there anything that I should have asked you? I feel like this has been quite a quick conversation, but it's really helped me. I just saw University of Washington as being these incredible experts in the field, and so it's fun for me to talk to you. But anything else that you want to make sure that we cover whilst we're on online?
I think the one thing that I would like to sort of point out that this is like trying to build a new technology, especially one that is so dramatically different than how people think about radios, has been a challenge and a learning experience. And what I really want to stress upon is that this is sort of the beginning of the journey for the technology and for us as well. And if you look back in history, like the way I like to uh, think about is Wi-Fi. Like nowadays, nobody has to do anything. Wi-Fi works seamlessly everywhere, but you would remember back in the late 90s when if you had to buy a router, it would take hours to set it up and it would sporadically work. And there's a lot of people who have worked day and night to get the technology to where we are. And the way I look at Backscatter is that it's interesting, uh, but it is a technology which needs more work, and we are on that path. And I truly believe that I don't know, maybe a few years down the line, 5 or 10 years, I don't necessarily know because nobody can predict the future, but I have the conviction that Backscatter would become mainstream.
Hmm.
It has its own set of challenges, and being sort of a scientist and who really believes in the laws of physics, I would like to point out that there are trade-offs with Backscatter. So it gives you that immense low power consumption, but the trade-off is that the range is less. So
Hmm.
you do trade off range for power consumption, and that's sort of the loss of physics I have to agree to because there is no free lunch. So I do want to sort of
Yes, exactly. No, I think that's really commendable to focus on where the kind of the development areas are, I remember when we were looking at it, our idea was there's sort of a bucket and you can fill it up, and so potentially the signal that you broadcast theoretically can be stronger than the signal that you're harvesting from. Whereas when you're doing backscatter, you're kind of reflecting back, and the signal will never be, because it can never be 100% efficient. It's always going to be slightly weaker than the signal that you get.
but actually hold that thought because I think one of the innovations that we did recently is
Mhm.
basically we have this technique called a reflection amplifier. So what
Yes.
that allows you to do is you can
Ah.
actually reflect more power than you get in.
Ah.
And the thing is, so if you want to go into specifics, so like if you're getting a very low amount of power, let's say minus 30 dBm, and that's basically 1 nanowatt. That's
Hmm.
very, very low amount of power. So what we have shown is that you can get a 1 nanowatt out, and reflect 10 nanowatts. So that's about 10 dB or like 10 times more power. But because you're amplifying 1 nanowatt to 10 nanowatt, the amount of energy that requires you to do is probably like 100 microwatts. Whereas if you have to transmit that amount of power, you're limited by your, I'm going to a bit more technical details here, but it's like the local oscillator would limit it. Even if you transmit 0 dBm or minus 20 or minus 30, there is a minimum amount of milliwatts of power you need to generate 2.4 gigahertz. But if you're only reflecting a nanowatt to 10 nanowatt, you only need 100 microwatt or so of power. So that's what I was trying to get to, is that as we
Okay.
develop these techniques, we can basically get closer and closer to what a radio can do with the techniques like reflection amplifiers to incrementally increase the range. So as an example, the board that I showed you, if you use the passive, then our Bluetooth range is, I would say, about 3 meters from a base station. But with the reflection amplifier, now we can approximately double it to about 5 to 6 meters. So doing these techniques and building on top of what folks have done would allow us to really get to a point which I truly believe in the near future, that backscatter would get pretty close to radios, or alternatively, there'll be a host of application where you can actually be seeing radios being replaced by backscatter and get to a point where either the devices have significantly longer battery life, or we can basically achieve this vision of battery-free IoT with a combination of all these techniques. Because like you pointed out at the conference, like we are racing towards a climate catastrophe, and one company, one technology won't be able to cut it. So we need this host of solutions to help us get to that point. And I truly believe backscatter would be, or should be, part of that arsenal.
And in the case of that reflective amplifier, then the supplementary power is coming from the battery or the supercapacitor or whatever it is that. So you haven't eliminated the battery, but you're just using the battery more efficiently.
Exactly.
Is that basically the benefit? Yeah.
Yep.
Yeah, I absolutely believe there's different tools for different jobs. And in a world of ambient IoT, which actually this is the first or second week where we've used ambient IoT in the name of the podcast. We've always talked about digital to physical convergence, but I think ambient IoT is actually a better description because it encompasses this world where the digital and physical are coming together. But it also implies a level of efficiency and cost reduction, which and it's just a cooler name. So we're using that, and we're using it because 3GPP is using ambient IoT as the basis of some of the new standards that we'll be rolling out in devices that will become part of the telephony standards that make up 5G and 6G. And so I think it's certainly not just going to be a world of Williot in that space. In fact, it can't be. We need different solutions that are competing head on, and different solutions that are complementary, which sounds like this what you're working on is. But it's all within this bigger category of ambient IoT, putting smart devices that can communicate into places where it was never feasible before because of cost and size. And so I feel like we're all part of a broader category, a broader community, trying to solve some really big problems with this groundbreaking technology. So Vamsi, I'm keen to hear what music you selected to talk about on the show. What were your three songs, or what was the first of your three songs?
So the first song is basically, it's a Hindi song. So I grew up in India, so it's called Yari Dosti, which by KK, so it translates into friendship. So that's one of my all-time favorite songs. I grew up listening that for a long time, like especially in my teenage years.
And where would you hear that song when you were a teenager? Was it on the radio, or would people play it? Or
So it's radio and TV as well. Back in my teenage years, MTV and Channel V, I don't know if you remember, but those were pretty popular. So I
Uh-huh.
used to definitely listen to them. And I also used to have the cassette back in the day when we used to have Walkman, the Sony Walkman.
I
Uh,
remember it well. I was just thinking about those the other day. What a beautiful thing they were. They're so amazing. Couldn't believe that they could fit music into something that small. And now
and
it's like gone to the
yeah,
next level. Well,
when I
that's cool. Yeah.
Yeah, I was just gonna say, when I think back, I used to have a Walkman, and then I upgraded to the Discman when you had to have CDs, and we used to burn
Right.
CDs. And then I
Yeah.
got my first iPod, I think it was in 2009 or 8 or 9, and that was a treat to have that tiny thing and hold like thousands of songs.
Phenomenal. So you had the one with the wheel, which you use your thumb
Yes.
to go around.
No, the first, yes, the wheel.
That
I
was
had
the
the
first
iPod
one.
Nano. So
Oh, the Nana. Yeah.
yeah, I had the Nano.
Those were incredible as well. In fact, I think my father-in-law just gave up his Nano. I mean, because it
Uh,
was just the perfect form factor for him. Okay, so that's song number one. What about song number two?
So song number two is "The Reason" by Hoobastank.
Okay.
That came out in 2003 when I was still in high school, and that's a song about sort of having self doubts.
Hmm.
So I kind of relate to that song because, like, as teenagers, especially in high school, you are sort of grappling with so many things, and that song really related to me. And actually, I don't remember the lyrics anymore, but there was a time when I remembered those. Like, I could sing the whole song, and I think that's one of the ones that I really, really, I still listen to Reason once in a while.
And I'm not familiar with the artist. I don't think, at least.
It's The band is called Hubas Tank.
Uh,
They're basically a rock band. Uh,
uh,
I think they're American if I'm not wrong.
okay.
Yeah.
Very good. All right. And what's number three?
Number three, I would say, is a bit of a cliche. It's Stairway to Heaven. It's
Oh,
one of the all-time greatest
yeah.
song, and the reason I really uh, remember it fondly is that used to be our go-to song back in college. So during my undergrad days back in India, like everybody would play it. I actually have a friend who would not leave, like every day. He would only exit his dorm room after listening to Stairway to Heaven, the full acoustic version for like 13, 14 minutes. And unless the song, like, we're like, dude, we are getting late, or like we are gonna miss the class. Nope. That has to be the way he starts his day. So that song,
Incredible.
I have so many fond memories.
Well, it's a wonderful piece of music, and
Yeah.
that's cool. And you were talking about Hindi music at the beginning there, and it just I don't know what your opinion is of our new prime minister in England, but we have someone who's our first non-Caucasian, a Hindu person as prime minister. I think it's amazing. I think it's like our Barack Obama moment. I'm not sure I agree with him not going to COP27,
Yeah.
but I'm kind of excited by that. I don't know what your opinion is on it, but
I haven't had the time to follow British politics, to be honest. I follow American and then Indian politics, and there's so much going on.
that's
But
more than enough. Yeah.
that's more than enough. But I'm sort of excited by sort of looking at his. Again, I think the bar wasn't that high with Liz Truss, so I think
Yes.
so. I think it's all relative after Boris Johnson and Liz Truss. I think this is definitely an improvement. I'm optimistic, cautiously optimistic. So yeah. So let's hope for the best for the UK and the world.
Absolutely. Whether you're on the left or the right, we all have a vested interest in Richie Sunak digging England or the UK, United Kingdom out of some of the challenges that it has. So, well, very good. Vamsi, thanks very much for your time. I've really enjoyed it. I feel like I got a bit smarter as a result of listening to you. So the osmosis is working. Thanks very much.
Likewise, it was great talking to you as well, Steve.
All the best.
Yeah, thanks a lot. See you. Bye bye.
Bye. Thanks for watching this clip from the Mr. Beacon Ambient IoT podcast here on YouTube. You can listen to this episode on iTunes, Spotify, or wherever you get your podcasts. If you enjoyed it, please like and share this video, and be sure to subscribe for more weekly videos. For more information about Wiliot and IoT Pixels, head on over to wiliot.com.